So can we start? Are you going to respond or I should just go ahead?
Yeah, we can start, Doc.
Sure. Okay. So if you are not talking, you just we are looking at Joseph. Joseph, is it Joseph Anand? Yes. Okay. So this main group chemistry, and that is the foundation of chemistry in the sense that we are looking at the basic concept of chemistry, which has to do with elements, and in that sense, substance, because chemistry basically is just the study of these elements. Well, in as a part of, and then I'm just going to summarize the whole kind of lecture into these 2 or 3 main groups. First, so today I'm just going to do the introduction to main group chemistry or main group elements. Then later we can talk of dividing the main group element into metals and then non-metals. And of course, if you're going to be treating non-metals, we'll look at the metalloids as part of that. So we can have 3 main categories: metals, semi-metals or metalloids, and then the non-metals. And that is what we're going to be looking at. Well, the halogens and then the noble elements are not quite interesting, with few elements that we can just address. So that's what we are just going to be looking at for this particular course. But the question is that why do we need to study main group chemistry, and what is it at all? So let me explain what main group chemistry is all about, or main group element. But when we say main group element, basically it's also known as elemental, or this representative element, or the element that represents the periodic table. And so if you consider the periodic table, we can group that, or we can just have some blocks of the periodic table, and that these blocks we can just understand what that blocks it. So from the basic concept of trying to understand elements, is just trying to understand that these elements have sub-particles in this element. So the element is made up of atoms of the same kind, and that these atoms are also having some sub-particles. Well, the classic kind of the classical way of understanding that says that we have 3 basic sub-particles of this atom. Well, in the modern chemistry says that we have more than that sub-particle, only that we can't really identify these sub-particles. And then these sub-particles that we know actually don't exist, but then they exist in the same form. So if we talk of element in the modern way will be the same as a proton, and that is just trying to balance itself. So that's where we have. So if we take the subparticle, then I mean the subparticle of the atom, then we talk of we having electrons, we having protons, and then neutrons. Now the protons and the neutrons are found in the core of the atom, which we call the nucleus. Then the electrons are evolving around the nucleus. And so once we have an atom and these atoms are going to be put together to form the element, then it means that the element is going to be having electrons. Now these electrons can be arranged, and by arranging them, we'll look at the probability of arranging these electrons or probability of even locating these electrons. Now, the probability of locating these electrons we call orbitals. So the probability of locating it when we treat the atom to be, the nuclear atom we know to be in a spherical form. So we're trying to locate that electron. So we start from the general form of the atom, which is like a sphere. Then we'll press the sphere by pressing the middle of it and orienting it in the 3-dimension. And then we'll try to press it and then pull it in the middle of it. So basically, what this probability list is the orbital. So we have what we call the sharp orbital. That's a spherical kind of shape. And that is quite difficult to notice the electron. So basically, for example, you take a ball and then you paint it white, and then you put a pen top, or like you sharpen a pencil, and then you punch just a dot on that big ball, say case 5. Now the probability of becoming or locating that dot is going to be quite difficult unless it is sharp. So we call that orbital the sharp orbital, or what you call the s orbital. Then we have the one that we coralize it and then orient it in the XYZ direction. So we have the p orbital, which we can orient it at the s, y, and then z. So we have ps, py, and then the pz. Then we have the diffuse type, which is like the cloven leaf. So that becomes a d orbital, because we can have the f orbital, which belongs to the Latinine, then the Artinine, which is a deviation from the d orbital. Now, when we arrange the orbitals, we arrange it such that they fall on a probability of locating this orbital. So that arrangement is what we call electronic configuration. Please, I hope you are following.
Yes, please.
Please, are you following? Okay. So this arrangement is what we are calling the electronic configuration. Please. Hello. Okay. So this orientation is what you are calling the electronic configuration. So when we write the electronic configuration, hello, can you hear me?
Yes, please.
Yes, sir.
Okay. So you see that some of the elements will have their electronic configuration, and that when we distribute the electrons, some of them will be ending with the s orbital, some will be ending with the p orbital, some will be ending with the d orbital, and then the f orbital. And so we group them into blocks. So we have the s block, those that belong to the s. We have the s block, we have the p block, we have the d block, and then the f block. Now, when we take the orbitals, well, we have 3 rules that governs us. We have the Avband rule, the Hund rule, and then the Pauli exclusive rule that governs us when we are writing the electronic configuration. But Hund tells us that there's no way an orbital can take more than 2 electrons. So the s orbital can just take only 2 electrons because its orientation, depending on no matter how you want to orient like a ball, it's in the SYZ direction, you will not see it. So it still remains 1. So for the s orbital, you can only have 2 electrons, so 1 and 2. So when we take the s block, so sorry, it's my cursor. Okay. So when we take the s block, we can have those that will be having 1 electrons on their shell, and those that will have 2, but then that's the s block. Now when we go to the p block, the p can be oriented into 3, s, y, z, and each of them takes 2. So it means that in the p block we should have 6 different kind of arrangement from P1 to P6. So we have 6 elements that falls on the P block. Then when we come to the D block, the D can be oriented 5 times. So if each of them is taking 2, then it means that we'll have 10. So in the D block, we have 10 kind of groups in that kind of D block. The F can be oriented 7 times. So each of them takes 2, so we should have 14 in all. Now, this is what we put together to form what we call the periodic table. We have history of people coming in to contribute to this periodic table, and that's one who made one breakthrough with the periodic table has to do with Mendeleev, Dmitry Mendeleev. He made a breakthrough in arranging the elements in this particular order. Of course, as at that time, he had less than 50 elements, so he could not arrange all the elements. After him, we discovered more elements. But then he made some predictions to how these elements that we discover should be arranged. Well, the initial kind of idea was that which element was discovered first was given a number. So that was what we call the atomic number. But later we realized that those numbers rather correspond to the number of electrons that these elements are having. So then the atomic number then became the number of electrons. Well, if the element is neutral, then it's the same as the number of protons. So the number of electrons or the number of protons is what you are calling the atomic number. Well, because elements are matter, we say that matter is anything that has weight and to occupy. So that element should have mass or weight. So we could calculate that and help us to calculate the atomic numbers, atomic masses. So we have the atomic masses for the element, which is basically the combination of the neutron number plus the atomic number. So the number of neutrons there plus the atomic number, you can just guess the mass of that atom. And the point is that once we can arrange them in their blocks, the S block and then the P block, the D block, and then the F block, that is what makes up the periodic table. Now, these 2 blocks, the S and the P block, were well known, and then they have been well studied. And so we call it the representative element, the S block and then the P block. They represent the periodic table. In any way, Dmitry did not do this table. Dmitry's table was combining this S and then the P block together as one like table. You are drawing a table. So you see how we draw a table. Please, I guess you get what I'm communicating. Not a table that we eat, like drawing something, figures and tables. So when we put these 2 together, that's what we call the representative element. And this is the main group element. Now, in between these 2, the S and then the P are some elements that are transitioning between the 2. So these elements behave like this S block, behave like the P block. So they are transitioning elements. And that in that transition element are those elements that are real elements. They deviate from the transition element. So we call them the Latinites, then the Actinites. And so if we understand the concept of main group, and that is what leads to the main group element. So we want to really understand or just also know more about these elements which are well kind of known. So this is what we mean by main group element. Now, it formed the foundation of chemistry because chemistry basically is just trying to use these elements that we have or know these elements that we have, studying them. And then, of course, why do we study them? We use them and then that kind of stuff. So if we want to really understand chemistry, then the foundation is just trying to understand this main group element. So it becomes the foundation for chemical principles. Any chemical principle you want to know about is just about this main group element. That's the S and then the P block element. These are just, and we have studied them. We know the number of electrons that they possess, the ones that are in their valencies, the ones that are in their core, and how they behave. So we even know the trends in terms of the periodic trends. We know how they are going to be behaving, like the ionization energy, electronegativity, electron affinity, atomic sizes, metallic characters, non-metallic characters. We just know everything about these elements that we are representing here. So they form the foundations of chemical principle. When talk of life, then this is what we mean by life, whether living or non-living thing. If we say living thing, we are talking of compounds that are made up of carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and some few halogens. These are what we call organic compounds. So when it is hydrogen and carbon, we say it's hydrocarbon. Now, when we add another element to it, like oxygen, then the oxygen is going to create another function. So in that hydrocarbon, we can just look at the bonding systems in that hydrocarbon, whether it's just a single bond, a double bond, a triple bond. So we have alkane, alkene, then alkynes. But then when we bring oxygen, then oxygen is going to be creating a function. So we call that the functional group. So in that case, you see that sometimes oxygen is going to bind with hydrogen. In that case, we'll say an alcohol is formed, or oxygen bonds with the carbon here, which can form ketone or aldehyde, or it can form both hydrogen or can combine with both hydrogen and then the hydrogen that leads to carboxylic acid. Now, when it's nitrogen, then nitrogen can be combined with oxygen or combined with hydrogen. When it's combined with oxygen, that's a nitro group. When it's combining with hydrogen, that is an amine, or depending on the number of hydrogens that is bonding, it can be called amide. So this is what we are calling the organic compound. Apart from these elements which I've listed, carbon, hydrogen, oxygen, nitrogen, phosphorus, and then the sulfur, and then these halogens, that is fluorine, chlorine, bromine, iodine. These are the organic compound. The rest of these elements which we find on the periodic table are all called inorganic elements. These are the non-living things. Is that okay? So if you take the periodic table and want to study these main group elements, then we are looking at the essentials of life, whether living or non-living thing, which makes up our ecosystem. That is just what we mean by that. Now, we can even know how much of them exist. By abundance, we can just know how much of these elements exist. And so we can know that, okay, on this planet Earth, we can survive, but then when we get to the moon, we don't have this element there, we don't have this element there, so we cannot survive. When we want to go to the Mars, that is it. So this is what we mean by the main group element. In fact, it is just leading to a lot of applications from the health sector to the agri to industry. I mean, talk of what application of science do you want to bring on board? Then this is just using main group element. Okay, so using these main elements here, that's the S&P block. That's what we just want to really know. And the knowledge of these main group elements has led to a kind of a diverse applications now, very diverse. So as part of our course, at a point, I'll be just looking at the applications and then the uses. So I'll just give you the common kind of chemical reactions and then those synthesis or how we can extract them. But then I'll be looking at more of these applications of these elements in that. And so if you look at it, then we can say that the main group element really dominates our everyday chemistry. Of course, because it's inorganic, we don't really do much mathematics there. So understand that we have, well, four main extreme of chemistry. and each of them stands on their own. We have organic chemistry, we have physical chemistry, we have inorganic chemistry, and then analytical chemistry, and they all stand on their own. So we have this inorganic chemistry, or the main group chemistry, really dominating in organic. It can also dominate in physical. So physical chemistry just basically apply mathematics to chemistry. And then for analytical chemistry, are analyzing substances. And so these substances are mostly the main group substances. So you can just imagine that if I say it's going to be dominating, you get to understand what I mean. So all aspects of life, from water to air to mineral to organic to biological systems, we can have these main group elements available. So as we speak, yeah, just or a lot of chemistry is going on as you are listening, and that even when you are not listening, there's still chemistry going. Most of these are just purely based on main group chemistry at play there. So how we control our emotions, our feelings, and these are compounds. Emotions are just compounds, which mostly because they are in our biological systems, they are organic compounds. And that we have a lot of these applications which I've listed there: cosmetic sprays, drugs, fabrics, paints, the fireworks that we have, hormones in our system, cleaners, vitamins, and baking, and those stuff. These are all as a result of main group chemistry. And so if you want to really get to understand that, then we should look at, I told you that that is the foundation of chemical principles. So if you look at it, the main group chemistry really teaches us the basis, the foundation. So if we understand these elements, which I've listed there, or on the periodic table, then basically it means that we should be able to understand our chemistry. So periodic trends, the bonding theories, the acid and base, which we normally see in analytical chemistry, for example, acid-base titrations, the oxidation states, electronegativities, and those kind of principles that we use are all based on this main group chemistry. Now, I'll talk of new and modern emerging technologies. These are all possible just because of elements. The computer, the phone is possible because we have batteries to support them. We have the screens, we have the semiconductors. And so if not, then it's just not going to work out. But then new technologies are possible just because we are now understanding and using our main group chemistry very well. And that's it's just even sustaining our lives. So talk of energy and sustainability, then this is main group at play. Well, in terms of area of research, we are still, though we know more about them, we are still looking at how we can use them in the application kind of form, especially say boron. Now we talk of catalysis, so looking at boron-based catalysis, which is quite interesting now, or the frustrated Lewis pairs, semiconductors, because technology is evolving, by just looking at that as well. It's relevant in the biological systems a lot. And as we move on, I will just be always looking at whether or not the element is useful for our system or not. So the biological system. So if I take any organic compound, then I'm looking at, so this organic compound with few sulfur and sulfur phosphorus compounds limited there, and then the halogens also attached to that. Our DNAs, the energies which we produce, the adenosine triphosphates, the sulfurs in the amino acids, these are all just main group. The point I want to bring on board is that main group basically is chemistry. Well, the foundation of chemistry, as I just said, all the others are going to be based in the argument from the understanding of chemistry. So you can be thinking of quantum chemistry or what we are now calling the computational chemistry. It's you need your chemistry before you can understand that. You talk of physical chemistry, you need your basic chemistry before you can understand that. If you talk of organic chemistry, you need that chemistry before you can. So that's trying to understand that will begin opening doors of chemistry for us. And that's what we just want to look at. So at the end of the course, at least we should be able to know our elements. Okay, so we are not going to look at, so I think, is it JHS or when did they started exposing us to elements? Is it JHS, eh? But I remember in the secondary school, they even make us, or they devise some song where you can know the first 20 elements. Is it SS or DHS?
GHS. It's GHS.
DHS, where
Yes.
I've forgotten the song, but then it's like, hello, hello, listen. Wow, wow, wow,
Yes.
wow. I forgot.
Hello,
Yes,
Helen. A
I.
little berry boy can now operate fishing net. Nana Magi, all singing prefect, can climb
Hey,
aeroplane.
yours is different from them. Now, teacher, no, I've been power. Maybe teacher, and the one. And it's quite interesting how there's some people who want to form because, for example, halogens, these halogens, FClBri. So it was one of my mates who made me just kept just off and it says that F is far, C is far, and then B is bra, and I is I. So facobra I, so that I'll know the halogens just often. Okay, so basically, at the end of the course, we should be able to know the main group element. And what you are going to be doing is that we're going to divide them into groups. So we have groups, the role of that. Then we have the column, which is period. So if you look at it, if I take hydrogen out here, I have 1, 2, 3, 4, 5, 6. So 6 elements in each group. Okay, and then we have group 1, 2, 3, 4, 5, 6, 7, 8. So 6 times 8 is how many? 6, 8,
48.
48. But then we'll take the group one by one and also take the element one by one. So by the end of it, we should just know the element of it without just memorizing anything. So we'll take, say, group 1. So this is group 1. This is group 2. Then we'll come to group 3, group 4, 5, 6, 7, 8. Okay. So we look at the group, the general properties of the group. Then we take the element each by. Is that a question? Somebody asking a question. Is there a question? Oh, please, if you are not asking a question, just mute yourself. So that's what we are just going to do. Now let's take the main group element and then try to understand that. Now, if you take the periodic table is put in classes and then in groups. So we have the column and then we have the row. Okay, so vertically and then across. Now, vertically is what you call the row, and then across is what you call column. So in our schools, we say that be in a row. So be in a cube, like a straight line. Okay, so this is a row. And then we have the column, which it's also across. Now in the row, we call it groups. So the vertical arrangement of the element, we call them groups. Then the horizontal arrangement, we call them columns. I mean, period. So in other words, the period basically shows us the energy levels that we have. And so if we start from hydrogen, and then of course it corresponds to helium, then we should be having 7 periods. Now, if we take the group, then we should be having 18 groups in the periodic table, excluding the Latinites, then the Artinites. 18 groups. But when we take the main group element, then we only have eight groups. So group 1, group 2, and then group 3 up to 8. So in the main group, we have 8 groups, including the transition elements. We have the 18 groups. Now, when we are numbering that, we have two ways of numbering the elements. We can number it such that we don't include a transition element, or we can number it and include a transition element. Now, we can use Roman numerals to differentiate between the two. So we have I for group 1, I for group 2, then the group 3, 4, 5, up to 8. Now, to differentiate that, we'll see that they use A for the main group and then B for the transition element. Okay, so we can have 1A, which is for the main group. We can have 1B, which is for the transition group. Now, if we want to number all together, to get the 18, then we use the Western numbers. That is 1, 2, 3, 4, 5. So it will capture here. So the last group will be the 18 number. So that's how we number the elements, the groups on the periodic table. Now, watch this periodic table very well, and then I will just maybe, I don't know if I should be asking questions or I should just go on. Now you see that well, just for color identification. Now we'll see the green colors. These green colors are the non-metals. So the periodic table can be grouped into these categories. Non-metals, the green one. So hydrogen, carbon, and those kind of are the non-metal, of course, including the halogens here. The blue ones are also kind of non-metals, and then the noble elements are also non-metals. Then we have the light green ones, which are the semi-metals or the metalloids. Then we have the metals which start from group 1, taking through the transition metals, and some in the P block, but then they are metals. Now, those that are metals in the P block, we'll look at their general form, but I want to mention that if you look at it, where the line, I don't know if you are observing my cursor move. So you see that the transition metal goes through that, and so aluminium is above that transition metal. Now, aluminium is a metal but belongs to the P block because it has a relationship with beryllium. And that relationship we call a diagonal relationship. So it has a diagonal relationship with aluminium in the sense that whatever compound aluminium is going to be forming, or beryllium is going to be forming, aluminium will form the same compound. So that's why it belongs to that P block, but then it is a metal. Now, when we come below that, gallium, then tin, bismuth, lead, and those stuff are also metal because they belong to the transition metal, which has been extended. So we call them the post-transition metals. Is that okay? Okay, so that is that. Well, if you see some of these ash, and then these three kind of element, three symbol element, means that they have not been discovered. These are predicted elements on the periodic table. They have not yet been discovered. So IOPAC says that we should have one or two symbols to represent the element. And so this is just to tell us that these are predicted elements. They are not yet discovered. Now we can then move on. So when we take the periodic table, as I mentioned, is comprising of the main group element, the transition element, and that of the Latinite and the Artinite kind of. So the main group element is the S. Yes, sir.
Yeah, please. Can you go back to the?
Is it this one? Is it this one?
Yes, please. Yes. After the barium, the boxes there. I don't know why are two boxes empty. There's no symbols on those boxes.
I don't get which box.
After group 2, at the barium side,
You
there
mean
are
this
two.
one?
Yes, please. Yes.
So this is the deviation that is led to the Latinum series, Atenine series. So this portion from atomic number 51 to 71 deviates, and this is what we call the Latinite. Then the 81 to 140 something, it's also called actinite. They deviate from the transition metals. So these two boxes here is actually an expansion which gives us the F block. So the F block is inside the D block. That's why we still don't know the shape of the F block. We have not studied these elements. We don't know the shape because it is inside the D block, that diffuse orbital. So the F block we call fundamental orbital. We are here to study them and then know them, but then they exist. Okay, so for example, this is europium. Well, most of these elements has the name of those that discovered them or where they were discovered. So we have americanium here. So it was discovered in America. We have this Belgium element here. So they are in transition metal, but they deviate. Now, even that in that transition metals, if you have ever paid attention to writing the electronic configuration, you will see that, for example, when we get to this, are you listening?
Yes, please.
Okay, so when we get to some, when we write that, we're going to see that some of the elements are going to be deviated. So, for example, the nickel group will deviate, the chromium group will deviate. We call it the abnormalities of the periodic table. And that's why these two space there is giving us the Latinite than the Artinite.
Okay. All right.
Okay.
Thank you.
Yeah. So while we group that, we're going to see that we have the main group element, which is made up of the S block and then the P block. Now, each of these has their own name. When we come to the S block, as I mentioned, we have two groups in the S block. When we go to the P block, we have 6 groups in the P block. Each of them is going to be having the family name. Now, the group 1 from the main group is called the alkali metals. The group 2 is called the alkali metals. When we go to group 3, which is the boron group, so that's we call the boron family. Then you go to carbon, which we call the charcoal group or the coal group. So carbon, silicon, and those. So this is it. Then we'll go to the nitrogen family, which we call the nicogens. So this is the nicogen family. Then we have the oxygens. So these are the oxygen family. Then we have the halogens. Then the noble elements. Well, the noble elements, most of them are gases, not all of them. When we cross the chromatin going, these are not gases, these are liquids there. And that they are noble because they don't really engage their inlet, they don't engage themselves in reaction, except one. So this guy here, where is my cursor? So xenon. Xenon is belonging to that noble element, but xenon can react with almost all the elements on the periodic table. And so it boils down to some of, I think in their candidates, they say that Ephebia, I think the Fanti say it very well. Ephebia Monsewum. Where I think the Ashantis want to say that they say that Ephebia Mensa Pachom Fie Mensa the correct word, the correct adage is Ephebia Monsewum. In every house there is a deviant. Okay, and that if you want to get to the Akanwa, they will say that if you be a mensem, like somebody who is too low. But that's not the context. So a xenon deviates from that. But then we have the rest being, and most of them are gases. That's why sometimes we call them the noble gases. So put together is what you are calling the main group element. And that is, so if we classify that, we have in that main group element, we can have non-metals, we have semi-metals, which we call the metalloids, and then the metals. Now, for the purposes of this course, I'll come to this. We just want to focus on the main group element, which has to do with the S block and that of the E block. But then we classify them into metals, metalloids, and then the non-metals. And so if you are going to be talking about metals, then we may include, of course, just for the purposes of this course, they are not main group, but we may include some of these metals in these transition metals or the post-transition metals to just look at those that are common with us, for example, the conjugate metals and then the poisonous metals. So in our part of the world, we talk of galamsey and heavy metals also. And so we'll look at those heavy metals also, which is poison in our system. And then you should understand that it's just going to be considering the main group element considers this kind of element. So we may consider other elements as part of the main group, but then they are not main, but just for this course. So like zinc, cadmium, mercury, which are some poison or some kind of useful to us, iron, and those kind of elements, the common ion elements that we know that are common to us, that we will just consider that. Now, when we consider these elements, they exist in nature. Well, if you look at these main group element, the element exists just based on the kind of bonding systems that we have. Ideally, we have two main extremes of bonding. We have what we call the primary bonding and then the secondary bondings. The primary bondings are the strong interactions. And for example, metallic bonding, ionic bonding, and then covalent bonding. Then the secondary bondings are the weak van der Waals forces that exist between molecules or in that molecule. So the inter and intramolecular forces, like lending dispersion or what we call dispersion forces, like the dipole-dipole moments or the dipole-dipole forces or the ion-dipole kind of force or the hydrogen bondings or the halogen bondings. These are the secondary kind of bonding. But most kind of bonds exist because of the molecule that they kind of produce. Where's my listen? Sorry, 1 minute. Yeah, sorry. So these bondings leads to these molecules that we have. So we have metallic bonding, which helps us to form metals. Now, metallic bonding basically is just a sea of electrons which are interacting with each other. Each of these elements have electrons at their valencies, which in the ionic form, they will be releasing these electrons. But then when they come into contact with another one that is also having these electrons in the valency, we call them sea of electrons. So they just interact with each other and form metallic bonding. Now, when we have a situation where one element can release its electrons, then the another element will be taking that electron, will be forming ions. So that will lead to ionic compounds. Then we have a situation where it's like NCNC. So we share electrons. This is what we call covalent bonding. Well, we can break it down, but then in our main group, we'll see that in as how the molecules are or these elements exist, They exist, of course, in their all forms, but then we have metals just because of metallic bonding. We have semiconductors just because of the, of course, covalent bonding that we have, and some molecules also just because of covalent bonding that we have. We have salts, and then these salts are also ionic bonding. So when we talk of salt, we are talking of ionic compounds. So this is how they exist in nature. So you see hydrogen existing as a gas, nitrogen as a gas, well, sulfur as, that's my guess, I think, so sulfur as solid, phosphorus is also solid, chlorine is a gas, bromine is liquid, iodine is solid. So it means that as you are going down, then you begin forming solid as much as possible. But then the noble element, you see them, all of them being gas up to xenon. When you cross xenon, so liquid gas from kratom xenon, then you'll be getting to the liquid kind of form. Okay, so this is what we see from the periodic table. And that's what we want to go through for this particular course. But we need to understand a little bit more on this periodic table. So we want to mention these trends, their properties that they possess, and then how we can just be mapping them on the periodic table. So if I should take any periodic table, I should just look at the properties, and then I should be predicting these properties. Properties like ionic size or atomic size, properties like the ionization energies, whether first ionization, second ionization, or third ionization energy, or electron affinity, electronegativity, metallic strength, reactivities, and those kind of stuff. So let's look at the periodic properties. So I'll just take them one after the other and try to see if we can just go through that. Now, I mentioned that the elements, so atoms making these elements have these electrons. Now we arrange these electrons, and then we realize that sometimes some of the shares, so if you take a share, we are talking of the energy levels for locating these electrons. In each energy level is a quantum kind of form in which we can contain these electrons. So when we take, for example, energy level 1, we can only look at just one probability. If we take energy number 2, we can look at 2 probabilities there. And the first energy will be having just one S. The S is the probability. Then when we take the 2, we can have 2S, 2P. Then when we take the S, we can have 3S, 3P, 3D. Then like that. I don't know if you follow that. So when we take 4, we can have 4 different probability, 4S, 4P, 4D, 4F. Okay, so that is how we arrange the elements. Now, each of these orbitals should take 2. That is if you look at the orientation. So S will take 2, P will take 6, all the P orientation, so 6. So what it means is that if you are arranging the elements, we'll see that the first energy level takes 2, then 8, then 8, then 8 in that kind of order. Then the rest will go to what we call the valence share, the valence energy level. Now, the energy level is what we also refer to as a period. So we are looking at the periodic properties in this kind of form. Now, first, we need to understand that the periodic table, as we have seen, is just a kind of an ordered. We have ordered the elements in such a way that they are going to be having similar properties. So when we take the group, it means that all elements that falls under the group should be having similar chemical properties. Are we okay? So,
Yes, sir.
okay. And that's if we are moving from, say, metals to non-metals. So if you take the periodic table, you see from group 1 to that of group 8, for the main group element, you see that you'll be moving from metals to non-metals. And this arrangement is quite distinct. It's quite distinct, and it gives us this kind of idea what would be the properties for that. And so the periodic trends basically shows us the atomic properties, and mostly what we can notice the energies which they possess, whether is it a metal that's a tendency to release electron, or is it a non-metal tendency to accept electron? So ionization, electron affinity, or the ability to draw much electrons to themselves. And that if we have the metals in the P block, why are they metals? Then I mentioned that, for example, aluminum and beryllium has this diagonal relationship. Below aluminum are post-transition metals, but then they are in this kind of block. So if we have elements being distributed, then they are being distributed based on the energy. And this is what will lead to what we call the energy levels or the electron shares. So we arrange them as the shares is going to be increasing. Now, when we take the shares, we'll see that as we go down the group, we'll be adding more energy level. So from 1 to 7. So the energy levels or the shares will be increasing. However, when we take across, then, or the columns, we are going to be seeing that the energy levels remains the same, but then the number of electrons are going to be changing. So it's a number of electrons which are going to be increasing, but then the energy levels remains the same. Okay, so in that case, what it means is that the number of electrons across the group is going to be increasing the valence electron, and then down the group is also the number of electrons are also in the same group. The number of valence electron will remain the same as we go down the group, because it's just the same. So if I take group 1, all the elements in group 1 will all have the same valence electron, 1, 1, 1, 1 each, but then their energy levels for possessing that one is going to be changing. So we should just note that. Now let's take these periodic properties and then we understand. So before that, if we take the metallic characters, what you will be seeing is that as we are going across, we are moving from metals to non-metals, so we'll just be decreasing the metallic properties in there. And then whilst we are going down, we are just increasing the metallic property because we are just even forming more metals across. So let's take these elements and try to understand that. Now I take the ionization, electron affinity, and those kind of stuff. Of course, we can calculate for these values, but then just using the raw values to just explain something. Now, when I take the atom or the element, as I mentioned, contains a nucleus, and then these electrons that are evolving around the nucleus. Now, there's an attraction between the nucleus and then the electrons. Okay, so that's kind of a nucleus, and then the electron attraction we call the nuclear effect. The effect is coming from the nucleus. So the positive is attracting the negative. So that's a nuclear effect. However, as you are increasing the shell, the number of electrons will be increasing, and so you are just going to be creating kind of barrier between other elements. Although the nucleus is going to be, the number of protons in the nucleus is going to be increasing, but then the number of electrons which are increasing are putting the electrons in far away. As I mentioned, the arrangement will be 2, 8, 8, 8 going. So it means that you are separating the electrons in 2, 8, 8, 8. So the attraction between that is going to be decreasing because there's what you call shielding effect. So the other electrons that are closer to the nucleus will be attracted more. So that will have a stronger nuclear effect, but then they will shield other electrons from getting access to the nucleus. So we have these two principles that we use in trying to explain these two, this principle of these trend, pure properties, the nuclear effect and then the shielding effect. As I mentioned, we can do calculation to get their values. We can calculate for the shielding effect. We can calculate for the nuclear effect as well. So I'll jump the calculation aspect of it. Now let's look at ionization energy, and then we'll just summarize this trend in that kind of form. Now, ionization energy is the energy which is required, okay, for an electron to be removed from an element. Now, again, let me send a caveat. In a modern chemistry, there is nothing like electron loss or electron gain. We don't lose electron, we don't gain electron. That we should understand. So that line that they were lying to us, growing up, we have seen that an atom cannot lose electron. It cannot gain electron. But then what happens is that, which the old chemistry or the classical chemistry could not really explain, but then say that it has lost electron, is that an electron can be excited. And when it happens, it moves from the lower energy to a higher energy. So in the old chemistry, it says that once you can't see the electron on that energy, means that it has lost. No, it has been excited. Now, with time, it will come back to its original form, and that is where we call it emission. Now, when it's going through that emission, it emits the energy. It releases the energy in the form of photons, a pack of energy which can be in the form of colors. So if you see red light, blue light, these are emission kind of, so the elements are releasing the pack of energy. That's what we are seeing, green, blue, and those kind of colors that we see. And so if you take the energy spectrum, what we call the wave group, you see the various corresponding wavelengths of giving the corresponding to the energy that we will possess. But let's still adapt to the old kind of chemistry. That's the ability to release electron requires an energy before you can release that energy. And so that energy is what you are calling ionization energy. Okay, so the energy required to remove an electron from an element is the ionization energy. Now look at it. As we move from our left to our right, we're going to see that. So let me use a proper periodic table so we can clearly get to see. Okay, so as I move from my left to my right, the number of electrons is going to be increasing, but then the shares remains the same. So if I take, for example, energy level 2 or the shell number 2, it means that it's just 2 shares there. And so if you go, it's just still 2, only that the atomic number is increasing, so the number of electrons are also kind of increasing. Sorry, who is this? Also increasing, but the shares remains the same. So what it means is that once the number of protons is increasing as against the number of electrons, and then it's all on the same energy level, then there's going to be a strong nuclear effect. Please, is that okay? So what it means is that there's going to be a strong attraction from the nucleus on the electrons which are on that share. So it means that as we move across, then the nuclear effect is going to be strong, and thereby reducing the, of course, the ability to reduce, to remove the energy becomes very high. And so it's quite difficult to remove because already there's a strong attraction between the nucleus and then the electron. So you need more energy before you can remove the electron. So as we move across, then the ionization energy is going to be increasing because as you are having strong nuclear effects, then you need more energy to remove it. Does it make sense?
Yes, sir.
Now, if you want to come down the group, as you are going down the group, you see that from 2 to 1 to, it means that we are adding more shares. Now, as you are adding more shares as the number of electrons increasing, then it means that the nuclear effect is going to be decreasing, and thereby the shielding effect rather is going to be increasing. So as we are going down the group, the shielding effect is going to be decreasing the nuclear effect. So it will be very easy to release electron or to take away electrons from this element than to take from this. So ionization energy going down the group will be decreasing as we go down the group. So if shielding effect increases, nuclear effect is going to decrease. If nuclear effect increases, shielding is going to be decreasing. And by that, it's easy to release the kind of electron which we have. So in natural sense, then what we can say is that ionization is going to be decreasing down the group, but then across the period, it is just going to be increasing. Does it make sense?
Yes, sir.
Okay. Then let me talk about, so, and ionization is taking the electron. So what it means is that we have species that we can take 1 electron, then we have species that we can take 2 electrons, and species that we can even take 3 electrons from them. So we have what we call first ionization energy, second ionization energy, and third ionization energy. So now, if I take the first ionization energy, for example, just for magnesium. Now, the first ionization energy is the energy which is required to remove the electron. Now, when I remove 1, I can't, it doesn't, so if we write Mg plus 2, it doesn't mean it lost all the 2 at once. It has to lose it one by one. So when it loses 1, it becomes a positive charge. Now, the reason why in chemistry, positive means you have taken away, negative means you have added, in the sense that it speaks opposite of physics. Because in physics, they even say that like poles will repel and unlike poles will attract. Now, when you come to chemistry, like poles will attract, unlike poles will repel. For example, organic solvents cannot dissolve inorganic salt. And then, so it should be an inorganic solvent dissolving in inorganic salt. So like salt in water, it will dissolve. Salt in oil, it will not dissolve. So oil is organic, salt is inorganic, it will not dissolve. So like poles are the ones that are going to be attracted. Now, when we say positive means you have lost, it means that the number of protons is now more than the number of electrons. By how much? You see that by extra 1 proton. So proton is given plus, then electron is given negative. So when we see, say, Mg plus 2, it means that the proton is 2 more than the electron. So we have lost 2 electrons. Is that okay? Then if we see negative, like say oxygen is 2 minus, what it means is that we have extra electrons than we have proton. So the minus there means that we have added extra 2 electrons to the oxygen. So that's where we have minus means you have gained, positive means you have lost. You have lost electrons, and so the protons are more than the electrons. So we add plus, and that is just that system. So when we lose 1, then you see that then now the protons are more than the electrons. So the attraction is going to be more than when we have not lost it. So we need more energy to even take the second one than we needed to take the first one. So the second ionization is always higher than the first ionization. And so the third ionization is even going to be higher than the first and second ionization energy. I hope the explanation is okay.
Yes, sir.
Okay.
Sir,
Now let's look at, okay.
In explaining the ionization energy, you said that it is the amount of energy required to take an electron from an element.
Okay.
Yeah, in that sense, can't we say that that element has lost electron, as you disputed earlier, that what you were
That
told in
that
the difference?
energy, that energy at the end will lose an electron. But the energy required to let it lose that electron is what we are calling ionization energy.
Okay, and I'm saying that the element that has lost the electron, can't you say that it has lost? Because you said that that idea when we're told
Oh,
that
I said that
electrons
I
are
want to give you a caveat. So we are still
okay.
doing the old chemistry. Like for example, main group is old chemistry. But I
Okay,
wanted you to know that we have modern chemistry, which makes us understand that the idea of losing or gaining is not even possible. When an element should
oh,
lose electron, the element will collapse because if the
oh,
proton is more than the electron, the element will collapse. And so, for example, our universe should then collapse, but we are still living in our universe. So we don't
sure.
lose anything. So
Okay,
that's where they were I trying to explain the energy, the conservation of energy. We can't create nor we can't destroy. But later they will bring the idea that okay, let's lose. But if you are losing means you have destroyed it.
sure.
So it's not true. But then we are still doing the old chemistry. So by the old chemistry, that's a simple concept that we can use that we have lost the electron, we have gained the electron.
Okay, sir. Thank you.
In fact, when it comes to the modern
Hello, sir.
chemistry, there's a lot of argument which we even have to we are still battling whether or not it is true, whether or not electron exists or not. And if it exists, where can we locate that electron? It's even another question which we cannot. And so some even bring the idea that there's even no proton, there's no neutron. It's just an electron that exists in three forms. So it's just
Sure.
like walking through a farm and walking at the same pace for quite some number of time. You see that you create a footpath. That footpath becomes heavy. That's why grasses or other weeds cannot grow there. So that place
Sure.
becomes heavy. So the electron passing through one place makes it heavy. And that is what the old chemistry was calling proton.
Okay.
And so that's let's leave it aside. Let's concentrate on our old chemistry. Yes, and I had somebody want to ask question.
Yes, sir. So, sir, I want to find out, just like you just explained, I want to find out that so if the electrons are going excitation, like what you said, or electrons are in the orbit. Now, if ionization is going to take place, which of the electrons are likely to be excited?
The valence.
Though you have explained the old, and you even try to touch the electron this thing.
Yeah, so
So
I
I just
said
want
the
to.
valence electron. We are looking at the
So like
valence.
in the old chemistry, let me finish and then say sorry for. Is it in the old chemistry, like you said, the valency electrons are the outermost shells. They are normally the ones that at the basic level we were told undergo the either losing or gaining. So in this case, is it the same thing, or this time any electron at all can be like taken off, like using the old chemistry? Please, that's my question.
Okay, so the valence electron. The valence means you are outside. So if you have electrons in indoor, electrons outside. Okay, so for example, you have students in your class and some student outside, and there is fire outbreak. Which one should escape first? Answer me.
The fire, it depends on where the fire is
So there's
emerging from,
fire,
but normally in
there's
the
energy.
whether in the classroom or outside, those outside will escape first.
That is it. So the valence electron will be the ones to be excited first. Then it will give room for those that are in the core to then start going to be excited, depending on the energy of the excitation. Is that okay?
Yes, sir.
Okay. So the valence electron is what we are dealing with here, and that's we are removing the valence electron. So if we say third ionization, then we are looking at those that have 3 electrons at their valency, and so they can lose these 3 and become positively charged. But then the energy involved is what we are looking at. The energy involved to remove that. You know.
Okay, sir, please. Hello, sir.
Yeah, I'm hearing.
Sir, please, if we use a normal phenomenon, like sometimes, so I would use the normal phenomenon to ask the other question about the attraction. You know, sometimes there may be a group, or like you are saying, like the electrons in a delocalized form. But like normal phenomenon, let's say a man and a woman, there'll be a lot of women, but the man will be attracted to a particular one. And then it will be like that particular one that is attracted to is the one that will be the force of attraction will be much greater, even though there may be people that are more closer to the man, but those ones will not have any attraction. If we bring it to the chemistry as you are saying right now, I want to just juxtapose it. It can happen that maybe the electrons, so I want to find out that the electrons, are they equally attracted by the protons in the nucleus, or it depends on the proton that is attracting to the electron? Please, are you getting me?
Yes, I get you. So give me 1 minute. I'll address here. Let me take some water. I'm coming. Yes, hello, thank you. Thank you very much. Yes. So let me say it this way. Now, the electrons are on different energy levels, which we call shells. So if I use your scenario, for example, then it will be like those shells that are closer. So the woman that is closer to the man will have an attraction. That woman is going to be called the core electron. Now that woman is going to be shielding the man, is going to be protecting the man from other women. That's what we call the shielding effect. So if there's going to be an attraction between the man and then another woman, then they should be on the same energy level. So if we say, okay, they are in the same classroom, the boy and the girls are in the same classroom, so there can be an attraction between all the classmates. But then the boy, it maybe is in class 4. Then he goes to see another girl in class 6 or GSS. The girls in class 4 will shield the boy from not getting to that class GSS girl. Do you get me?
Yes, sir.
Yeah, so the girls in class 4 will shield the boy. So that's what we call shielding effect. But then there's going to be on the same energy level, there's going to be the nuclear attraction. So it happens for electrons on the same energy level. Once you cross a different energy level, the attraction is going to be decreasing or increasing depending on how you are closer to the nucleus.
Okay.
Okay.
Okay,
So
sir.
that's
Yeah.
ionization energy. Now we look at the, of course, as I mentioned, we have calculations in doing that thing, but then let me just skip that calculation aspect. Maybe on the slide you see that calculation part, but then you can ignore it. And because we teach this in level 100. So I just bring it in just to recall that. I don't think, did you people do Chem 107? I don't think you did
No, sir.
107 general chemistry. Okay, so that's first year course. So we teach the calculation part and then. Okay, now let's look at another energy. So we are looking at the energy which they can lose. How about the energy which is involved? That's adding on electron. So that will be the electron affinity, the energy which is evolved when we are adding on electrons. It's evolved, it's being released when you add on electron. Now again, since you brought in the concept of male and female, so let me also use that again. Now look at it. There's a strong attraction between a boy and a girl. Then there's another boy who wants to remove the girl from that boy. Well, what it means is that the incoming should have enough energy or enough money to deposit before he can leave, the girl will leave. If there's a strong attraction. Well, if there's not strong attraction, any form of engagement will let the girl go. But then if there's a strong bond, a strong interaction, a strong attraction between the nucleus and that of the electron, then for you to add on another one. So if, for example, a man wants to marry two wives and he's already married to the first one, if he's bringing in a second wife, if he doesn't really make a huge investment or a huge deposit for the first one, when the second one comes, there'll be a kind of repulsion. They will fight out till they break, their marriage just breaks off. So that man should be able to bring in. So the more you deposit, the more the first one is going to be accepting you, because there's a strong attraction between you, the first, and then the man. So electron affinity is just the energy which we require to add on the a kind of extra electrons to another system to make it negatively charged. Now again, look at the periodic table again. Then we'll yes. So if you look at it, as I move across the group, then the nuclear effect is going to be, I mean, across the period, the nuclear attraction is going to be strong. And so if I want to be adding on electron, then I just need more energy once I'm going across the group. Do you follow that? What it means is that the tendency or the energy required for this element to add on an electron to this element will be higher than adding on an electron to this one. So electron affinity will be increasing across the group, but then here there's already kind of a fight between the wives. So adding on, so somebody says that if your wives are disturbing you, marry another one, then that's another one will come and create solve your problem for you. So there'll still be more for you. Don't need any energy to put in there. So the shielding effect is high, and so you don't need any higher energy to be adding on electron. They are just having more energy levels, more shell, and so we can just, so electron affinity again is going to be decreasing down the group, and across a period is going to be increasing. That's what electron affinity is about. Once we need, I mean, there's an attraction. When you are adding on electron, there's a huge energy, if, I mean, a huge energy which is going to be released once you add on that energy. Are we okay? Are we okay?
Yes, sir. So yes, sir.
Okay.
So the can you, in the course of explanation, can you also use the stability of the, because at the basic level sometimes we use the stability of the elements or the atoms, like Aufbau principle was talking about the instability some of the electrons, because they are not able to fill the outermost shell, they are not stable, and then so on. So because of that, it is like you can add the electrons to them, but those who are having more, and then they just need them to go away. Can you also use that in the explanation to the electron affinity?
Well, that would be wrong. If you say
Okay.
that they have more, they want to, every element on the periodic table is stable. Every element is stable. If they are not stable, they will not exist. That's the first thing. Now, what you also notice is that once they have more electrons, does not mean that they want to give out electrons. They want to rather be taking the electrons. So we'll come to electronegativity, the ability to draw electrons to themselves. Once they have more, they want to draw electrons to themselves. Okay, so that concept or that idea that you are bringing is not correct. Okay, now
Thank you, sir.
what we need to understand. Yes.
Hello, Doc. Hello.
Yes, I can hear you.
Yeah, Doc, please, you made a comment that every element on the periodic table is stable. What about the radioactive elements? Because we know that those who are radioactive undergo disintegration because of their instability.
But then they exist as that element. So maybe I should rather define what stability is all about. So again, if this element is exposed to an environment, a surrounding, so we have what we call systems and then surroundings. So we have energy exchange between the system and then the surrounding. The stability I'm talking about is when, for example, in a closed system where there's no exchange between energies between the system, which is the element, and then its surrounding, then we are saying they are stable. Otherwise, when you expose this element to its environment, like oxygen, air, and those, then they are going to be non-stable. When you expose them to surroundings where temperature is going to be affected. That's why, for example, if I take this element, mercury, okay, mercury is solid. But then when you expose it to temperature above 25 degrees, it begins to melt. But does not mean mercury is not stable. So I'm looking at it in the context of it is not engaging its surrounding. So radioactivity comes in when the element is exposed to another surrounding. Is that okay? So we begin seeing that it begins decomposing. So in that case, then all these elements, when exposed to its surrounding, are going to be engaging in one form or the other in reactions. So that's what we call chemical reactions. Then they are not stable. So chemical reactions will then deal with the electrons moving up and down, exchanging between the surrounding or the neighboring surrounding and itself. Then we will say that reaction is happening. So that's where we can say that, okay, this element is not stable.
Yeah, Doc. Hello.
Yes, yeah, I can hear
Yeah,
you.
yeah, I understand the explanation, but we also basic chemistry learned that it's like the radioactive elements are not affected by external conditions like the temperature and the rest.
So what makes them radioactive?
Oh, but for them, we also learned that they emit radiation spontaneously or they are
So what
bombarded by particles.
let's don't try to confuse yourself. What is radiation? Radiation is what?
Hello?
Yeah, I mean, what is radiation?
Radiation is the particles or energy emitted by the element.
Are you not coming back to the same thing? So we are then exposing the energy, which is an external factor.
Okay. Okay.
So if that without that energy, then that element will not be radioactive. So the energy can be alpha, it can be beta, it can be neutral.
Okay.
So when we talk of radioactivity, that is alpha radioactivity beta and then the neutral radioactivity, meaning you have exposed this element. That is why it has started engaging that kind of energy.
Mm.
Okay, so what I'm trying to, we take the element in a closed system where you are not exposing it. So when, for example, when I take francium, I know francium is radioactive when I expose it. So we keep francium in the container, then you see them drawing the radioactive sign there. So you see still francium sitting there, not going through radioactivity, not going through decomposition. Okay, so that means that the element there is not engaging any kind of surrounding. So that element is intact. Once you expose it to heat, whatever, radiation, whatever, then you see it decomposing
Okay. Yeah, thank you very much. So we can just conclude that all elements are stable under a closed system.
under a closed system. And
Okay.
the closed
Thank
system is when no temperature is present.
Okay. Thank you.
Okay. Yeah, so electron affinity, I think that is okay. Okay. Now the next one is the atomic sizes. Of course, it follows the same trend where you look at the nuclear effects going to be increasing, thereby shrinking the size. So the same number of shares, but then the number of protons is increasing as against the number of electrons increasing. So there's a strong attraction between the nucleus and that of the electrons on that valence share. So you're going to see that the size across the period is going to be decreasing. But then as we go down the period, I mean, in the group, you see that the size is going to be increasing because we are adding more shares. Nuclear effect is going to be decreasing. Shielding effect is going to be increasing. And so the sizes of the atoms are going to be increasing. Are we okay? Well, the same explanation can be given to ionic sizes. If you take the same kind of not changes, so it means that if an element loses an electron, the string it shrinks it more. If it gains an electron, it expands it more because there's going to, depending on the period, please, depending on the period. So if I take, for example, Cl minus, okay, and that compared to Cl itself, then it means that the Cl minus is going to be bigger than the Cl itself. Are we okay? But then on the same period, if I take, say, Mg2 plus, they are on the same, so the size of the Mg is going to be shrinking whilst that of the chlorine is going to be. So the more we gain the electrons on the same period, again, the caution here is that it's on the same period, because if we change to a different period, the electron will be more. So the sizes is going to change as we change the period, as we go down. So the size is going to be increasing. So on the same period, then, so if we say that we have, say, so Mg2 plus, which makes it 10, and then we have, say, sodium plus, which is also 10. Then, of course, we are looking at, we're writing the electronic configuration, we're going to see that they will all be on the same period. Now, if they are on the same period, then across from left to right, then the sizes is going to be increasing. Then from top to down, it is going to be decreasing. Are we okay? Now we can talk of the metallic properties and then the non-metallic properties. I've mentioned that as we move across, we are decreasing the metallic properties. And then as we go down, we are also, I mean, if we go left to right, we are decreasing it. Right to left, we are trying to increase the metallic properties. So what it means is that the non-metallic properties becomes opposite of that metallic property. If it is not a metal, it is a non-metal. So if from left to right, I'm decreasing the metallic property, means that I'm rather increasing the non-metallic properties. Is that okay? Please confirm if am I off?
You're
Okay.
on, sir. You're on, sir.
Okay. The next property I want to discuss is electronegativity. Again, we can
Electronegativity.
from Louis Pauling gives us a clear way of calculating for these values. So we have values calculated for the electronegativity, but electronegativity basically is the tendency for an element to draw electrons to itself. Okay, so the ability, well, the energy is when you draw electrons, you are going to be evolving the energy that is electron affinity. But the electronegativity is the ability to draw electrons to itself. Now, the basic explanation will be that you see how the noble elements behave. They have 8 electrons at their valency, and that makes them inlet. That makes them non-reactive. So every element want to draw electrons to themselves to behave like this noble element. We call that the Lewis theory. So in every reaction or any compound formation, you see that these elements are going to be engaging themselves such that they will have 8 electrons at their valency, or 2. For hydrogen and helium, they will have 2. So we have duet and then octet. So we have the octet rule, a duet rule for hydrogen and then helium. Otherwise, the rest of the main group element is going to follow that octet rule. Well, with few exceptions. We have 3 exceptions to that octet rule. We have the incomplete octet, the expanded octet, and then the odd number, that's radical. So you get to have element being radical, you get to have some element not having up to the 8 electrons, that's the incomplete, and you have some even exceeding, like sulfur, exceeding the 8. But all of them want to be having these 8 electrons at the valence. So what it means is that the more electrons that you have, it becomes easy to draw another electron to you so that you'll be complete to have the 8. Okay, so the lesser it becomes quite difficult. And let me try to. So to draw electrons to themselves. So when you take the periodic table, you see that electronegativity is going to be increasing from my left to my right, because as you go from left to right, the number of electrons are going to be increasing. And so the tendency to draw other electrons to themselves becomes high. So they need it more. So those having 7 can easily draw, and they have that strong ability than those having 6 and those having 5 and that kind of order. So electronegativity is going to be increasing from my left to my right. And of course, as we go down, it is going to be decreasing. So as we are adding more shares, it's going to also be decreasing. So that magnitude is what we can, Louis Pauling helps us to calculate that. But then it's just like the picture I'm showing you. The guy having this magnet to have that strong feeling for the electron, all because he wants to also have it complete share and behave like that. So we can calculate this electronegativity negativity. Please, is that okay?
Yes, sir.
Okay. So that is just that. Now we have other properties. So we can look at the trend. These are what we call the periodic trends. And then we can just make some conclusions there. So electron affinity, we can talk of the ionization energy, we can talk of the metallic characters and those stuff. But we have other properties which these elements engage in. For example, how they form structures. Okay, how they're going to be forming structures and how they form bonds and those kind of reactivity using the reactivity series, where we notice that some elements are much reactive than the other. Now, how they form structures, of course, we have atoms combining with the same atom to form elements, so we give it an elemental symbol. Now, elements also combine to form compounds. So the compounds, we can have the ionic or the molecular compounds, which we give it the molecular formulas. Now, molecular formulas will combine to form reactions. So we write the equation, chemical equation. Now, in that molecular formulas, we can predict some structures from of course, from the Lewis system. We can notice that we have the octet rule from the Lewis dot. We can have the octet rule, know the octet rule and see how they combine using their electronegativity, so we can form the compound, whether the compound is ionic, metallic, or covalent bond, or know the valency there. And that will help us predict this. So we can have what we call the valence bond theory. We can have the valence share electron pair so okay. Yeah, it's possible because of the bondings that we have, and I've explained that kind of part. But then other properties like reactivity, we'll see that when we have these elements and then they want to engage themselves, then there's going to be some changes with this element. It's either, so if when it meets with something. So one element is going to meet with another element. There's a tendency that there's a possibility that they have to change before they can engage themselves. Otherwise, it will not happen that they will form a compound. Okay. So for example, if you have a dry paper, you just want to bend that. Well, the dry paper is going to bend quickly than when that paper is wet. You agree? Please, you agree?
Yes.
So what it means is that the dry paper is much reactive than the wet paper. So that's in a simple kind of form. So we can just see that that's just a form. But some elements are quite reactive than the other. I don't know the kunu kunu I'm hearing. Is it from my side or people joining? Okay. So some elements are kind of reactive than the others. So we have what you call the reactivity series, which shows how some elements are quite reactive than the other. So, and of course, reactivity basically has to do with the electrons that are in the valence electrons or in the valence electrons, how they are going to be engaging their environment, how easily can they engage, how kind of difficulty can they engage, will lead to what we call the reactivity. So some are very reactive than the other. So if we take the reactivity series, you see potassium is quite reactive than sodium, and that the other begins decreasing as we go down the group. So we have this reactivity series. I mean, not group as in the periodic group, but then we're in the reactivity series, we'll see the main group kind of reactive than the transition metals, if you want to put it that way. So that's something which we should just bring on board. Now, to just summarize what I'm trying to do today is just the meaning of why
Sir,
we need, yes.
please, why is potassium more reactive than the sodium? And even fluorine is also more reactive than even iodine or bromine, even though all of them
I
have the
didn't
same.
get you.
I said, why is potassium more reactive than the sodium?
Hello,
Yes, sir.
I didn't get what you said.
What I'm saying is that when if you look at the reactivity series, you could see that the potassium comes first. It means that it is more reactive than the sodium.
Yes.
Yes, and my question is why?
Why, in terms of, so let me take you back if I can get a periodic table to just, yes. So if you look at it as we go down the group, then reactivity is going to be increasing on the same group.
Yes.
So what it means is that cesium should be fast reactive than rubidium, and francium should be reactive than that. So sodium, potassium should be reactive than sodium. Sodium much reactive than, lithium in the same kind of group. Do you get me? So reactivity is going to be increasing as we are going to be having more, in the sense that as we have more electrons in more energy levels, that electron is quite like I don't care electron. It can just engage already. There's this shielding effect which makes it lose like it's not having any kind of connection with the nucleus. So any form of any little trigger, it want to just get excited.
Okay, so what about the halogens? I mean, from fluorine to iodine, which one is more reactive?
So as we go down, we become more kind of engaging. Now, again, we can also be using the kind of sizes to also come in here. So in terms of reactivity, we'll be saying that they should be getting, so as we are going down, we have gases turning to liquids, and of course, in terms of their molecular form. So again, look at this. These are purely metal, so it's easy to understand. But here, these are gases, turn to liquid, turn to solid. So solid are less reactive than gases, liquid also less reactive than gases. Okay, so the phases also matters in terms of reactivity. Well, that's why in the reactivity series, we don't list all the elements because we use sizes to explain that so the size has to do with the valence electron. Then we use phases. The phase of the element should also be considered. So gases are much reactive than liquids. Liquids are also much reactive than solids. So reactivity, we are looking at how fast the electrons can move. Now in the gas phase, electrons are already moving fast with the element than in the liquid phase.
Okay. All right, thank you.
Okay, so then if we come to the P block, then we have to be looking at the phases and then their sizes. If we come to the metal, then we are looking at, of course, their sizes, which has to do with the electrons, which are just going to be volatile. So we list the electronegativity series. There you can see why we are considering that. Where's my electron? Please, are you okay?
Yes, sir. Thank you.
Okay. So that's the reactivity series. Okay, now let's try to summarize that if that's okay. So we have a lot of, elements in our disposer now. which are the representative elements which are quite useful to us in the terms of medical field. We have just listed some common elements and where we find them and where we can use them as well. So that's just a basic kind of introduction for us. Now for the well, I don't know, yours is the distance type. So if we want to look at the main group element, then I'm going to take the periodic table, group it into three kind of parts: metals, metalloids, and then non-metals. Now this will be the baseline for taking. Also, I said I'll take the of course properties, physical properties. Then I look at how they exist. They are all forms. And now we can extract them. Then there are reactions that they engage in or the interactions that they engage in. Some of them we can synthesize them in their compounds can be synthesized. How we can apply them. So this is what we're going to be doing for all. Yes. Yes, sir.
So please, your screen is off.
Please confirm for me. I don't think so. Okay. Thank you. So let me check my screen. Is it back?
Yes, sir.
Is it back?
Yes,
okay.
Sir.
So thank you. Yeah. So this is what we are going to be going through for the rest of the course. Well, at a point in time, if I'm taking them in group by group, it gets boring. So what I'm going to do is that I'll take the group and look at their general properties and then their general chemical reactions. Then the rest will be the uses and the applications. So when I take the individual element, I'll just look at their uses, that's the applications, and then so I'll give you each kind of group their general reaction because it's just going to follow the same kind of reaction scheme. And then the compounds that will be forming. So I'll just give you the general compounds and then the respective kind of elements. We just keep that and then we looking at just the application.
Yes, please.
Please, am I on? I think so. Okay, so that's just what we want to be doing. I have some few minutes. I think on the timetable we're supposed to go for a break and come. I'm not going for a break. I'll just do the general properties, and I think next week we are not meeting. The following week then we meet. And so and don't worry, we'll still finish what we have to finish. So there's no pressure here. Okay.
Yes.
So I'm looking. Yes, sir.
Please, before you wrap up, and then like I want to find out from you is that if there are some factors that determines the elements, either reactivity or negativity, because the reason why I'm asking this is that naturally, you realize that even though, let's say for example, like my link is breaking.
Yes.
So I'm trying to find out if there are some factors because that determines an element's ability to either exhibit more negativity or reactivity, because sometimes you see in naturally there are some women who are even more reactive than men, and then so And then we just taught us that the reactivity, it increases down the group and then decreases across the period. So it means that naturally an element in a group 1 is expected to react more than an element in group 7, if I am right. So I want to find out if there are other factors that influence the reactivity. Please, do you get me? Hello? Hello? Hello?
It's gone off. It's gone off.
I think this thing, that's why normally from previous years, I don't want to be using the code link, because once there's problem with the host, everything goes off. So the one asking the question, I don't know if you want to speak now or you want to type it so that I can read and address you. I didn't get the question at all.
Okay, what I'm trying to find out that hello sir, can you hear me?
I can hear you. I can hear you.
I'm trying to find out that if there are other factors that determines the whether an element becomes more reactive or is able to draw electrons to its of the negativity. Because naturally, no, like I'm trying to use natural phenomenon. Like if you take maybe a man, let's take the man as the metals are the group 1 and then group, and a woman. There are some women who are more reactive than men. But per the explanation that you gave right now, it's supposed to be the other way around. Like a element in group 1 supposed to react more than an element in group 7. So I am trying to find out from you if there are other factors that also influences the reactivity or the ability of the element to either draw electrons to itself, like electronegativity, or to react in an ideal situation.
Okay, I get you. So let me. I think so. We are where's my slide? Yeah. So we are taking us back to this one, right?
Yes, sir.
Okay. Yeah. So let me just look at it from this. Now, for you to say that an element is reactive, number one, reactivity has to do with the electrons, movement of electrons. And so number one thing is that for an element to be more reactive, number one, it should have fewer electrons. Fewer
Okay.
electrons in the sense that it want to, if it is just the main group, then of course it can just, these fewer electrons will allow it to lose it if it is a metal, or if it has more, then it want to draw electron to itself. Now, number two is that when we have electrons that are far away from the nucleus, when they are far from the nucleus, that means that if you have more shielding effect, that electron makes it reactive because it's already far. And so reactivity becomes higher when the electron is far. That's why, well, let me go back to my periodic table. So that's why I said that if you take the periodic table, I'm trying to find you one. Sorry. So let me, yes. So if you look at the periodic table, for example, for these metals, you're going to see that the electron for the francium here is going to be far from that of electron from cesium. So a reactivity for francium is going to be higher than that of the cesium, and then in that kind of form. So when the electrons are far away, it makes it more reactive. And then when the electrons are also kind of few at the outer kind of valence, it also makes it a kind of reactive.
Very reactive.
And then when there's also a very strong kind of nuclear effect, it also makes that element reactive. So for example, that's why I came here. And so apart from you using the physics, you will see that electronegativity, for example, I mean, that kind of nuclear effect, the sizing is going to be very high, meaning this is going to be of course, they are in the gases, but this is going to have a stronger nuclear effect as compared to this element. Just showing you something. So fluorine and chlorine. Fluorine is going to have a stronger nuclear effect than chlorine. Therefore, fluorine will be much reactive than that of chlorine. And of course, they are all in the gases form. You get me?
Yes, sir.
The noble element will not react at all, aside xenon. But then you look at it and say, okay, now factors that you should consider. When there's a strong nuclear effect, the element is going to be reactive. When the electrons are also far away, the element is going to be reactive. And again, when you take the same on the same kind of period, the fewer the are the outer shell also make it more kind of reactive. You get me?
Yes, sir.
Yeah, so if you want to be using like the periodic trends, then you're going to be saying that, okay, if I move from my left to my right, then reactivity is going to be increasing because the nuclear effect is going to be strong. As you move from my left to right, nuclear effect will be strong, and so reactivity will be increasing. Are we okay?
Yes, sir.
And then if you go down, the electrons are going to be far. So as you are going down, reactivity is also going to be increasing. Because the electrons are going to be moving far. So reactivity for these systems, then reactivity is going to be increasing. For this particular system, that's the non-metals, reactivity is going to be decreasing. So we don't have like a uniform, like the electronegativity will just be uniform throughout, move up and down. For reactivity, it depends where you stand. For metals, reactivity is going to be increasing as you are going down the group, and then across it will be increasing. For non-metal, it is just going to be decreasing. Are we okay?
Yes, sir.
Okay. So that's if that's okay. So then, well, let's come to our metals here. I just give introduction then. We pause. So let's look at metals. Now I'm talking of general metals. Now metals can be in a form of a pure metal. If I say pure metal, that means that the elemental form, or when the metal is mixed with other metals, it becomes alloys. So we have combinations of metals called alloys, and then when we don't combine them, we call them pure metals. Of course, if you look at metals, well, let me ask you some general properties of metals before I come to talk of the combinations of metals. Can you list 3 people giving me properties of metals? How do we see that this one is a metal? Both physical and chemical.
Okay, one is that they are malleable.
Malleable means?
Malleable means they can be beaten into shapes.
Thank you. Next person.
They are ductile.
Which means?
Which means they can be drawn into wires and then other things.
Okay. The next one.
They conduct heat and electricity.
They are good conductors of heat and electricity. So that's chemical. Thank you very much. And of course,
metals are shiny.
And that's what's the term? If they are shining, what's the term given to that?
They are
Lustrous.
Bristol.
Well, lustrous or lustrous, L-U-E-R. So is it lustrous or lustrous? Okay. Well, we said that we can combine metals to form kind of alloys. Alloys like brass, like bronze, like steel, and those kind of forms. So, for example, when we talk of brass, what is the combination of metals here? Brass. What's the combination? Which metals are combined there?
Yes, sir.
Yes.
It's copper and zinc.
Copper and zinc. Okay, thank
Yes,
you.
sir.
How about bronze?
Tin and copper.
Copper and tin.
Copper and tin. Well, how
Yes,
about
sir.
the steel?
What?
Steel.
Carbon and iron.
Carbon
Yes,
and iron. Well, if I'm marking, I'll give you 90%. It's not only carbon and iron. So we have manganese there. We have small amount of sand, that's silicon oxide. We have phosphorus, and then we have some trace amount of phosphorus and sulfur also there.
Okay.
So it's carbon.
Okay, sir.
Well, huge amount of it is coming from iron. To just 2% of carbon, 1% of manganese, and then more trace amount of silicon, oxygen, phosphorus, and sulfur. That's what we call bronze. Now, if we take the periodic table, we've mentioned that over and over. So I just skip. We look at the properties that you've mentioned. So we said that they are lustrous, they have high densities, they are in solid, solid at room temperature, meaning 25 degrees. So it means that below that mercury is solid. Well, if you cross 25 to 26, some like cadmium becomes liquid. So not only mercury is liquid metal, we can, depending on the temperature, we can have other metals melting as well. Then they are good conductors, they are malleable, ductile, brittle, high melting point. If they are liquid, high boiling point, they have good valencies. In the chemical forms, we see them becoming more electropositive, meaning they can easily release electrons. And that's why we call them metals. They can just release electrons and become positive. In that case, according to Lewis, they are basic. So we see one group from that metal, the group 2, we call it the alkaline earth metal. So a base earth metal. Lewis base is electron pair donor. So they can donate 2 electrons, so they become a base. Okay, so most of them are kind of amphoteric. That means that they can behave like acid and base when they react. So the oxides are both amphoteric. You see them forming more ionic compounds in nature. They form ionic compounds. So metal combining with non-metal, they form ionic compound. They are hydroxides. They form also metal hydroxides and those kind of reactions as well. But in nature, we will see that most of these metals are found in the earth crust. So in the middle of the earth, we have a lot of these deposits in the earth crust. It's unfortunate that we don't really pay attention, but these minerals or these metals is what makes a country rich. But if I say that, then we should start bowing our head to shame. So Ghana should be one of the richest country in the world because it has almost, we are going to be discussing that, almost all the common metals that we know, we can find them here, but yet we are still poor. So that's just another discussion. But we get to have a lot of them in the earth crust. So elements like magnesium, sodium, calcium, iron, aluminium. So we have a lot of aluminium deposits here in our country. We have like 3 towns still mining aluminium in the form of bauxite. But then we don't really convert them. We just export the stone they'll go and bring their pure aluminum, then we will rather change it into the sheets and then the pans that we have. Well, silicon, which is the sand, we have a lot of oxygen deposits in the earth crust. A lot of that. That's why we can survive on the earth. Okay, so if you look at it, then all the elements that we're going to, especially the metals, we can also get them from the sea water as well. A lot of them are deposited there, where we can have the minerals there, and then they are all forms. Okay, so this is what we want to be doing. We'll take the metals in general. So we'll take the metals starting from this group and then considering the conjugate metals, okay, copper, silver, gold, and then those that are useful poisonous metals, zinc, cadmium, mercury as part of it. Then we'll consider the post-transition metals, which belongs to the main group, and aluminum as well. Then we'll look at so that's the zigzag line, show you the end of the post-transition metal. Then we also have another zigzag line, which talks about the metalloids, and then the rest will be the non-metal. So I want to take the group 1. Is it okay to proceed or to halt? Shall I proceed? Hello?
Yes, sir.
I should proceed.
Yes, sir.
Okay, so I'm just looking at the properties, then I'll just stop there. So I'm taking the group 1, the group 1 metals. I just come and look at the general forms of the group 2, and then we'll take them one by one. So the group 1 metals are called the alkali metals. In other words, the ash metals. Okay, so that's the general name for this group 1 metal, which is the lithium, sodium, potassium, rubidium, cesium, and then francium. These are the group 1 metals. So if you want to keep that, that is their names and then their symbols as well, with the exception of these two. That's the sodium and potassium, which has their names from the old names. So sodium is having an old name called nantium. Potassium is having an old name called crantium. And so their symbol taken from the old name, sodium, Na from nantium, potassium, K from crantium. So that's their names and their symbols that we can just see. Now let's look at their general kind of form. So if you look at it, the sodium and potassium and most of the common metals that we engage ourselves as humans. That's the most common that we look at that. But all these metals are going to be having this silver white kind of nature, with the exception of the cesium, which is golden yellow, and then the francium, which is greenish. Okay, but again, once you are getting down the group, and then we get exposed them to our external force, they become radioactive. So we don't want to be engaging such elements at all. Now in their general form, lithium, sodium, potassium, rubidium, cesium, and then francium. I don't know if you can see my slide, but then if we take lithium, lithium is so soft. So you see the woman there with a knife. Okay, so we say that women are soft. Please, not the general form, because we've seen that some women are very hard, but in general form, women are very soft, except few. Except few. Just the hard ones are also there. But in general, women are very soft. That's lithium, the metal which is so soft that you can cut it with a knife. It's a metal, but it's so soft you can easily cut it with knife. Then we have potassium. Now, if you look at the picture, what's that man doing? Can you engage me?
Yes.
That character is stepping into water. Do you see that?
Yeah.
Yes, please.
And when look at his face, when he step into the water, what happens?
It is like he has leaped up.
It looks like he doesn't like the water. Like during Hamatan, and then you ask people to go and bath.
Oh yeah,
And
yes.
it's men that behave that way. Women don't have problem with that. So men don't like water at all during cold time. Okay, so that's sodium. Sodium, of course, is found in ocean, of course, and then the earth crust. But then sodium reacts vigorously with water and produces heat. And sometimes hydrogen gas and sodium hydroxide is extracted from water, but it doesn't like water at all. When you put sodium there, for example, you have sodium hydroxide. I don't know if you have prepared sodium hydroxide solution before. When you fill the bottle, you feel hotness. It's an exothermic reaction.
Okay.
So it produces that heat. So sodium, in its pure state, will react violently with water. It will react with water, although, but then in a violent kind of way. Then we look at potassium. Potassium K. It looks like there's this character that is more intense and dangerous. You see him.
Yes.
So that means that potassium, of course, it can react with water even more violently than sodium will do. But potassium burns. It burns like in the lactic flame. So that color, I don't know how you call that color. Is it purple or the correct color? They say is lilac color. But I don't know, the common color you say will be purple, eh? Okay, so it burns in that lilac flame. So when exposed to a flame, you see this color. Yeah, it's quite burning. And you see, once there's a little bit sweat in your palm and you drop sodium, potassium metal, it starts burning. I mean, your hands, you feel that burning sensation in your hands. Well, if you are moving down, then you are becoming more even dangerous. So rebellion, you see, it portrays that flame and then that explosive arrow. So rebellion basically means red. And so this is the metal that explodes when it comes into contact with water. So again, you see when you are going down the group, its reaction with water. Potassium react violently. Sodium react violently. Potassium is even more violently than sodium, and rebellium is even more than potassium. Then, if you come to cesium, it is going to be more. Francium, we don't engage francium because once you expose it, you are exposing it to an environment, external force, then it becomes radioactive. So we don't engage francium. Okay, so rubidium means red, which is more explosive when it comes into contact with water. Then cesium is more reactive. Again, reactivity is going to be increasing down the group because we are going to be having more kind of electron at the valency, and so reactivity increase. So cesium is much reactive than rubidium, and francium will be more reactive than that of. So we'll see cesium. Now, if you see cesium, you see that, of course, it looks like it's burning. And then when it burns in blue flame. Okay, it's burning with that blue flame. Now, francium is unstable, very unstable, and in dissolving, then will be giving us this green glowing kind of light. So radioactive francium is much radioactive and unstable in itself. And that francium destruct or destroy itself once it has been exposed. You see it destroying itself, meaning its radioactivity is very fast. It decays very fast once it's being exposed. So that is the general form of these group 1, the alkali metals. Now the next is the alkaline earth metals. Alkaline means base. They have 2 lone pairs to be given out, and that they are found in the earth crust. These metals are found in the earth crust as in nature. This is how they exist in their metallic form. Now, in their general properties, we'll see beryllium, magnesium, calcium, strontium, barium, and then rhodium. Okay. Now, if you look at the first character there, beryllium, what can you say about beryllium? Maybe I should rather engage you. What can you say about beryllium?
Very excited.
Very excited, and then you look at the hands there. You look at the hands, it looks something. Oh, don't you see this greenish, this bluish something? It gives some correlation to that element. It's very lightweight but very strong, like a stone. Very strong, and it reflects the character of its posing like a strong girl. But of course, it's not that strong as compared to magnesium. Okay, so magnesium depicts that you are looking at somebody who is bright, very intense flame. It burns very intense. So when you are doing practical, when you are burning magnesium, the caution is that you don't look directly to that magnesium burn because it can hurt your eye. Okay, it gives a very bright light at a very, like the flash. Those cameras that had flashes. Now because of digital world, those flashes don't really, but those of you are a little bit old. The magnesium bromide or the silver bromide flash that they use, then it can, when the picture comes, you even see your eye being red. Okay, so magnesium burns with that very bright white flame, which I think we're doing that practical 207. So I had to change. So this year I've changed the practical because it burns the students' eye where we're dealing with this exothermic and endothermic reactions. It burns, and then we caution students not to be looking at that kind of flame. And it's very difficult. When it catches fire, we don't use water to quench it. We rather be fueling it more to burn more. We use sand. When magnesium catches fire, we use sand to quench it, not water. And again, I think you'll be doing safety in the lab. You see the fire tetrahedron and what it means to make fire, and so you can quench fire. It's not every fire that you go and fetch water and put it on. And that's the issue. Let's know. Now, look at calcium. Well, calcium is this nice lady there showing the bones. Well, what it means is that our structure, our shape, our form is basically because of bones. So, and bones are made up of calcium and a little bit magnesium. So it's very crucial. Calcium is very crucial for our teeth, for our bones, which gives us the skeletal form that we have. Okay, so we should get to have. So the various shapes, the facial kind of arrangement is just because of calcium. And we get to have a lot of calcium from our dailies. That's a milk, and then those dietaries which contains calcium source. So calcium helps us to be strong by giving us strong bones and those nice shapes that we have. Okay. Well, we can also look at strontium. Well, this girl being happy, jumping up and down, and we see a lot of these fireworks, especially in Scotland. Okay, so they do a lot of fireworks so that they get to have red color, yellow, especially when it's getting to the ending of the year there. So it's part of jubilation. So means that strontium gives us this nice colors when we are dealing with this fireworks. So for celebrations and those stuff, we get to have they use strontium a lot. We'll come to strontium. We will see that strontium is what they use in our phone screens, and then TV colors, the color TVs that lets to the screen day. So we had the LCDs, the liquid crystals, which has now been changed to the diode. It was strontium that we had. Okay, then we have barium, which looks like a muscular figure there, which is green and heavy, very, very heavy. So it means that this is quite reactive, burns easily in air. Once exposed to air, it begins to burn. And it burns in this greenish kind of flame. And it's very kind of heavy. We consider that as part of heavy metal, but again, we'll be getting to, because it's quite reactive. From there, we are getting to the radium, which is much radioactive, and it glows with that radiating kind of energy there. And so it tells you that there's a Rex. If you get closer to that man or that element there, you will get yourself into trouble. In the overall, or as suggested as a summary, we'll see that the alkaline earth metals are quite strong and stable. And that if you look at them, if you are going down the group, you see that their stability is just going to be decreasing whilst their reactivity increases. So when you are going down, they are not stable, but then they are quite reactive because they react very fast. The other element which we'll be considering is aluminium, which we get from bauxite. So if you have not seen a bauxite before, I show you how bauxite is. If you see this stone, you throw it away, but that's bauxite. So that trace of ash something there is what they extract to get this aluminium metal there. Then we talk of gallium, we talk of indium, we talk of tin, and then titanium, lead, and bismuth, and then the polymer. Now, I just summarized the general properties of these elements that I've listed there. Number one is aluminium. Aluminium is strong but very lightweight. So if you talk of our cans, aluminium cans that we use, like the can Coke, the can malt, these are the aluminium cans that we have. Of course, aluminium is expensive. But then in terms of food, once aluminium forms or reacts with oxygen, the oxygen protects the aluminium. So the oxides of aluminium are quite stable and that they don't engage in any form of reaction. So we use it for food. Okay, so the aluminium cans are quite common, and we use it also in plane and some constructions like the aluminium sheet. Those of us who are along the coast, they recommend that we use aluminium sheet or slate because of the sea salt. It can easily corrode that metal, but so aluminium stays longer than the zinc or the ones that they have mixed with aluminium. They call the allo zinc. The aluminium is it can survive these corrosions that we have. So there you can see that aluminium is strong. That lady there drinking from that, we use it for cans. Now gallium is somehow showing a melted spoon in a hot tea. You see that? So he's going to drink tea, but then it starts melting. What it means is that gallium can melt when, of course, when exposed to a temperature above 29 degrees, it begins melting. So that's also another metal that can be liquid. A solid room temperature, when you increase to 29 degrees, it begins melting. So when you put gallium in your hot tea to melt it. Okay, so that's just that. Now we can also see Indum. Now the Indum here basically portrays somebody who is flexible and then is singing. I guess you can see what I'm just saying. And so what it means is that easily, Indum can easily be bent, and then it also emits this lustrous noise sound by like screaming kind of stuff, very loud sound when you are dealing with Indum. Then the next is tin. So when we get to tin, I'll just caution you on how bad. So we use tin, tin tomatoes and those kind of stuff. So tin is widely used because aluminum is expensive. We use tin to replace them in canned and in food production. However, tin, when exposed to oxygen, forms a tin oxide, which is quite poisonous. So they coat it. They coat it with a paint. So if you are going to be buying, say, tin tomatoes and you go, then the tin tomatoes are smashed. Please don't buy it. When it has smashed, meaning the paint, there's a tendency that the paint which they coated it has removed. Once it has removed, there's a kind of reaction which has begun with your tin tomatoes. Or you go and then part of your tin tomatoes has started rusting. The can has started rusting. There's a tendency that it started from inside and then you are seeing it outside. So you don't buy it. You check the expiring date, check the best before time. We'll get there, then I'll explain what you mean by expiring and then best before time. But then we should be very careful in tin products. So the advice is that when you are using tin product, once you open it, the product that is in must all get out. Otherwise, you have exposed it to reaction now. So you take your tin tomatoes, you open it, all the tomatoes inside must go out. I see people, after they have removed, then they'll pour oil on top. Of course, what you want to do is that you don't want the tomatoes to engage the oxygen to start molding. But then the tomatoes is reacting with the tin, which you are not aware. So you take everything and put it in a plastic and store in a fridge or store it in water that it can also sustain for some time and throw the can away. Here we don't do recycling of cans. Otherwise, outside, just take it to recycling. Okay, that is just that. Then we look at the titanium. You look at that figure there. If you ask you're going to say that you see this lady that looks like a ghost. Yeah, a ghost figure there, which is moving like a serpent. Okay, so what it means is that the titanium really tarnishes and corrode quickly, and then it can just get into more or less like disappearing mode whilst it is still available. Okay, so it is highly toxic. We should just send that signal because it vanishes. You see, oh, there's now no titanium. Once it has gotten contact with you, it is there and it's going to eat into your system. So very dangerous when you are dealing with titanium. Then lead. We'll see this lead man standing close to RIP, rest in peace. Okay, very dense, very bulky kind of guy. But then history tells us that it poisons us unaware. And unfortunately, Africa, for example, Ghana has become a dumping site for lead. And lead poisoning is extremely poisonous. I mean, it's very dangerous because this lead has a charge of +2. And our system, what keeps us alive, also has a charge of +2. I mean, iron. Iron in porphyrin ligand, which we call hemoglobin, is what keeps us alive. And so, and if you check the reactivity series, lead is reactive more than iron. So what it means is that lead can quickly go to replace all your iron in the system. And that's what we call lead poisoning. It can create what we call lead stones. So lead poisoning is quite kind of something that we need to get interested in. Well, bismuth is quite useful. If you talk of the colors that we see in our ladies using makeups, then there's bismuth there, giving us these purple colors and those stuff. Then we have the bismuth medicine. That's a bismuthol, or the petobismol, which is the so-called pink medicine. I think when you go to the drugstore, that's what they call pink medicine. So it's used for stomach upsets, the acids that comes in. And so bismuth is quite useful to us. I mean, it's not poisonous. We can have access to that colorful kind of metal there. Okay, so that's the general form of the metals which I'm going to be looking at. So the next time we meet, I'm going to be talking about the alkali metals now. Take them in general form, look at their general reactions, then take the element one by one. And then, just as I mentioned, the reaction one by one. So that's why I look at the general reactions, so it doesn't make it boring. Then I'll just look at the applications of that. So I want to pause here and then ask for questions if there is. Hey, am I off?
No, sir, you are on.
Okay, so any question? So we'll meet if I check the timetable, it means that this is someone who have a
Hello.
yeah, so yes.
Hello. Hello.
Yeah, I can hear you.
Yeah, Doc, please, in your statement, you said that lead is more reactive more than iron, and I don't understand. Because when you look at the reactivity series, you see that iron is above lead. So why is lead reactive more than iron?
Maybe it's sorry, sorry. Please come again. I was just engaging someone.
I was saying that when you look at the reactivity series, iron is above lead on the series, and those elements above easily undergo oxidation and they easily lose
Yeah,
electrons.
so sorry,
So
did I say lead?
you say lead is reactive more than iron.
No, sorry. Lead is rather less reactive, but then
Okay.
it has its own way of sneaking. Oh, please. Okay. Yeah, it has its own way of sneaking in to make it behave more like the ion F2 plus. You know, the Fe can change from Fe2 plus to Fe3 plus. That is the oxygenation process. And then the deoxygenation is when Fe2 plus 3 plus changes to Fe2 plus. Now, in that changes, we are moving from a more stable to a less stable. So in that case, then lead has a nice way of sneaking in to replace that ion, not like reactivity form. In terms of reactivity, then you are correct. The ion is rather reactive than lead. Is that okay?
Yeah, it's okay. Okay.
Is it out?
Hello.
Yeah, you just mute and then talk, or I can show. Oh, please, who is talking? Just unmute and then talk. Not who is talking. Just unmute and then.
Okay, sir.
So, Paul, if you want to talk, talk. So, Paul, if you want to talk, talk.
Okay, please, I want to know among the items there, which of them can we get the rubidium from them? That's the item from the screen.
You mean the list that I've made here? This ones? The pictures I'm showing you or what? Oh, please, the pictures I'm showing you, basically I'm showing you batteries, which is coming from lithium. Then I'm showing you salts, which can be potassium and then the sodium, salt, and then potassium also from banana. I didn't show you lithium. From the rubidium, francium, and then cesium, I'm just using this picture to show how explosive that they are. So when I've not started dealing with this one, so that's what I'm trying to say here. Are you okay? Okay.
okay.
Another question if he's offline. Yes.
Okay. Another.
Yes. Any others? Okay. Then see you if there are not kind of questions there. Okay. So see you next time.
Please, can we get the slides?
Yes, of course. I'm going to send that to you right away.
Thank you, sir.
So how I'll do that is when I have a platform which I can get all of you there. So I don't know if you can add me to a platform so I can drop it, or one of you, I can give you my WhatsApp line. Hello, Majoria. Please, is that okay? So that I can be dropping the materials. So I have to drop the materials for this.
Sir, please, we have a platform.
Yes, Abdi, type here my WhatsApp line so that you can add me. Is that okay?
Yes, sir.
So I think this is my WhatsApp line. 64697738888. Okay, so this is my WhatsApp line. You can add me. Please, have you seen it? I sent it on the chat. Have you seen it?
Yes, sir.
Okay. So that's my WhatsApp.
Thank you, sir.
Okay, Doc.
Thank you.
I said genetics, psychology, and genetics.
So I don't know. Atomic physics. And I course in one.
The general code for specific people. Paul, you are a physician. Anna, Paul, I am physics beer.
They were having I don't know if you are other physics students or I didn't give it a young community and better me.
Because I call for all of us another for you, the physics student. Please, atomic physics for physics minor. Oh, okay. Oh, okay. Thank you. Okay. Okay. Thank you. That's a Paul.
Sir Cash. Sir Cash.
On the Christmas mood, yo.